All right, class, now we're going to start Chapter 9, which is all about hypothesis testing. We have Chapter 9 left and Chapter 10, and then we're done. So we're in the home stretch. So the first thing we need to talk about is the fundamentals of hypothesis testing. So let's consider a product called gender choice, and it claims to increase a woman's chance of giving birth to a baby girl from the usual chance of 50% of the time, right? How could we determine whether or not this claim is true? How might we test that? So, if the claim is false and we take a sample of maybe, let's say, 100 women, if the test is false, half the women using the product will have girls, or really close to half. And if the claim is true that gender choice does increase your likelihood of having a baby girl, then significantly more than half of the women using the product will have girls. So those are the two possible outcomes when testing this gender choice claim. Now, what constitutes significantly more, right? We say this product, gender choice, significantly increases the likelihood of having a girl, okay? If the sample consisted of 100 girls, 100 women, and 100 randomly selected babies, and we found that 52 of them were girls, would we think the product worked? No, I'm not really confident, right? 52 out of 100. That's 52%. That's really, really close to 50%. And we only took a smaller sample of 100 babies. Maybe we would need to increase that sample. Now, what if 97 out of the 100 babies were girls? Would we think that product worked? Yes, right? That means 97% of the women who took this product had baby girls, okay? Now, let's get a little more in the weeds. What about 64? If 64 of the babies in the sample were girls, would we think the product worked? Is 64 significantly more than the 50 babies we would expect? Well, it's quite a bit, right? It's more than 2. So let's think about this, okay? We can answer such questions as whether 64 baby girls would be significant through hypothesis testing. We're going to be testing our hypothesis, okay? So the first thing we're going to assume is that gender choice does not work, right? We're always going to assume that what we were hoping for doesn't happen, okay? And that's going to be what we call our null hypothesis. So in which case we would expect to get what percent of the populations to be girls? So we'd expect 50% of the population to be girls. Next, we want to assume, let me move this up a little bit. All right, next we want to assume to calculate the likelihood of drawing another random sample in which 64 or more of the 100 babies are girls, right? So we're going to use this assumption to calculate the likelihood of drawing a random sample when 60 more of the 100 babies are girls, right? We have a sample size. We're going to be using the distribution of sample means, of sample proportions, right? Because 64 out of 100, 64% is a proportion. So, if we find that such a sample with 64 or more girls is fairly likely to have occurred by chance, what can we conclude? Okay? If we find that this is fairly likely to have occurred by chance, we can conclude gender choice works. Oh, sorry. Is fairly likely to have occurred by chance, what can we conclude? So if it's fairly likely to have occurred by chance, then gender choice does not work. If we find such a sample that is unlikely to have occurred by chance, right, there had to be some outside cause, this couldn't randomly happen, then we can conclude gender choice, that product we talked about in the second slide, works. Okay, so it needs to be unlikely to have occurred by chance. Okay, note that if we have enough evidence to support a conclusion, that does not mean we have proven our conclusion. So here's how we formulate our hypotheses. So a hypothesis is a claim about a population parameter, such as a proportion or a mean. And we conduct an hypothesis test This is a standard procedure for testing a claim about a population parameter. So there are always two hypotheses in any hypothesis test. There's going to be the hypothesis that gender choice does not work in raising the population of girls born, and the hypothesis that gender choice does work in raising the proportion of girls from 50%, right? That's what we would normally expect. So we've always going to have two hypotheses. So the null hypothesis is the claim that gender choice does not work, okay? Under this hypothesis, what would we expect the population proportion of girls born to women to be? Well, we already said it'd be 50%. So let's use P to represent the population proportion. How would we write the null hypothesis? So my null hypothesis would be, we write that H naught, that's what that 0 means, H naught is when P equals 50%. So this is my hypothesis that gender choice does not work. So when I conduct my sample, my population proportion would be 50%. For my alternate hypothesis, that's the claim that gender choice does work, right? Which means we would expect the population of girls to be greater than 50%. So I could write this alternate hypothesis. We write H sub A for our alternate hypothesis would be that my population proportion is greater than 50%. Okay? Greater than 50%. That would help us prove whether or not, or help us come to a conclusion that gender choice works or does not work. So H naught is the starting assumption for our hypothesis test. Okay? We have the population parameter equals its claimed value. Okay? The null hypothesis always has an equal sign. Always, always, always. That's so, so, so important. The null hypothesis always has an equal sign. Okay? Our alternate hypothesis is the claim that the population parameter has a value that differs from the value claimed in the null hypothesis. So differs can take on a few forms. So it could be that the population parameter is less than our claimed value. We call that left-tailed. It could be that the population parameter is greater than our claimed value, just like in our gender choice example. Or it could be two-tailed. So the population parameter does not equal our claimed value. So these are the three forms that our alternate hypothesis can take on. So in each case, let's identify the population parameter about which a claim is made. We're going to state the null and the alternate hypothesis for a hypothesis test and indicate whether it's left-tailed, right-tailed, or two-tailed. Okay? Left-tailed uses a less than, right-tailed uses a greater than, and two-tailed uses a not equal to. So, Nissan claims that the Leaf, this is a car by the way, Nissan claims that the Leaf, oh it says it, darn, that is an electric car, has a mean range of 110 miles between charges. A consumer group claims that the mean range is less than 110 miles. So my alternate hypothesis is that there's no difference. So it's going to be that I have a mean equal to 110 miles because this is the adversized claim, right? There's no different from the claim. My alternate hypothesis would be that my mean is less than 110 miles. Because I'm using a less than, this means it would be left-tailed. All right, let's take a look at another example. So in each case, again, we're still identifying our null hypothesis and our alternate hypothesis. So the Ohio Department of Health claims that the average stay in Ohio hospitals after childbirth is greater than the national mean of 2 days. So our alternate hypothesis is that there's going to be no difference to the claimed value. And our alternate hypothesis, they say that the days spent in the hospital after childbirth is greater than the national mean. So we're going to have the mean is greater than 2 days. This would be right-tailed. Because we have a greater than, it's going to be right-tailed. Next, a wildlife biologist working in the African savanna claims that the actual proportion of female zebras in the region is different from the accepted proportion of 50%. So now we're working with a proportion. So Our null hypothesis is there's no difference from the claim. So our proportion, we're going to use a P because we're using a proportion. Proportion is 50%. And my alternate hypothesis is just that it's different from 50%. It doesn't matter if it's less. It doesn't matter if it's more. It's just going to be different. So this is going to be our proportion does not equal 50%. And because it's a does not equal, this would be a two-tailed. Okay. So there are possible outcomes of a hypothesis test. So there are two possible outcomes. One, you reject the null hypothesis. This means we have enough evidence to support our alternate hypothesis. Two, we do not reject the null hypothesis. That means we do not have enough evidence to support our alternate hypothesis. There is no accepting in hypothesis testing. We'd never say, oh, we accept the null hypothesis, we accept the alternate hypothesis. No accepting, just rejection. There's only rejection in statistics. So, for each of the three cases from example 1, let's describe the possible outcomes of a hypothesis test and how we would interpret these outcomes. So, for my niece on leave, I could reject the H naught. That means I have enough evidence to support my alternate hypothesis, right? That would mean I would have found that the mean is less than 110 miles. I could also not reject my H naught. That means I do not have enough evidence to support my alternate hypothesis. That means if we did the test, we would have found that the mean range was tolerable within 110 miles. All right, so in this case, my alternate hypothesis was that my null hypothesis was that there is no difference between the national mean of 2 days and the mean in Ohio. So if I reject H naught, that means I have enough evidence to support my alternate hypothesis, which was that hospital stays are greater than 2 days. If I do not reject H naught, I do not have evidence to support my alternate hypothesis. So I probably in my study found that the stays of women in Ohio met up with the national mean of 2 days. There was no difference. Then for when we were working in the African savanna, right? If I reject my H naught, that means that from my study I found that the population of zebras was different than 50%. And if I do not reject H naught, that means I did not find enough evidence that the difference between the population of zebras, that population of zebras had a population of females different than 50%, right? If I don't reject my H naught, there are 50% of the zebras are female. So how do we draw conclusions from a hypothesis test? How do we decide if we should reject or not reject the null hypothesis? Well, we're going to look at statistical significance. So if the probability of a particular result occurred by chance, right, 0.05 or less, we say it's statistically significant at the 0.05 level, right? So that's a probability event occurred by chance is 1 in 20 or 5%, right? If the probability of a particular result occurring by chance is 0.1% or less, then we say it's statistically significant at the 0.01% level. So that means the probability it occurred by chance is 1 in 100. Note, we never use anything less than the 0.05, anything greater than the 0.05 level, okay? Right? We only use 0.05 and 0.01. Those are our two types of statistical significance. If you need to go back and look at what it meant to be statistically significant, feel free to flip back to section 6.1, where we first introduced that idea of being statistically significant. So, we decide the outcome of a hypothesis test by comparing the actual sample result to the result expected if the null hypothesis is true. And we have to choose a significance level, okay? If the chance of a sample result, at least as extreme as the observed result, is less than 0.01, then we say it's statistically significant at the 0.01, and that offers strong evidence to reject the null hypothesis. If the chance of a sample result, at least as extreme as the observed result, is less than 0.05, then we can say it's statistically significant at the 0.05 level, and we'll reject the null hypothesis. Okay? If the chance of a sample result occurring by chance is greater than 0.05 or 0.01, that's when we do not reject the null hypothesis. Don't do it. So, let's consider our gender choice example, okay? Where we had a sample proportion of 0.64, so that meant 64 girls out of our 100 babies, right? And we were under the assumption that our null hypothesis P equals 0.05 is true. I find the result that we have a 0.0026 is the probability of this occurring not by chance. So based on this, should we reject or not reject the null hypothesis at the 0.05 significance level? Yes, we can reject our null hypothesis at the 0.05 significance level. Note that this is also less than 0.01, so we could reject our null hypothesis at an even better significance level. That's what we want at the 0.01 significance level. All right, so now we're going to take a look at how to make a decision in our hypothesis test to either reject the H0 or do not reject H0 based on p-values. Okay, now what are p-values? So p-values stand for probability value, and we're going to represent this with a capital P. It's not going to confuse with a lowercase p for population proportion. So for a hypothesis test of a claim about a population parameter, the p-value is the probability of selecting a sample at least as extreme as observed. Okay? So assuming that the null hypothesis is true, a small p-value indicates the sample result is unlikely, and so we would therefore reject the null hypothesis, right? It means it's unlikely to have occurred by chance, so we can reject the null hypothesis. You always want a small p. Next, a large p-value, that would be greater than 0.05, indicates the sample result could easily occur by chance, so we cannot reject the null hypothesis. So we always want a low p-value of 0.05 or less in order to reject the null hypothesis, right? Meaning we have enough evidence to support our alternate hypothesis. So let's take a look at another example. So you suspect a coin may have bias towards landing more often on tails than heads, and you decide to test the suspicion by tossing the coin 100 times. The result is that you get 40 heads and 60 tails. A calculation, not shown here, this will be given to you, indicates that the probability of getting 40 or fewer heads in 100 tosses with a fair coin toss is 0.0028. Okay? So what's the p-value, and state if the sample result is statistically significant or not. Okay? So our p-value is this. This is our p-value. Our p-value is 0.0228. Okay? Is this statistically significant at the 0.01 level? No, because this value is greater than 0.01. But it is statistically significant at the 0.05 level, so we can reject our null hypothesis at the 0.05 statistical significance level. So let's put it all together. Here's our hypothesis test process. So step 1, you're going to formulate your null and alternate hypothesis and determine whether you're going to need a left, right, or two-tailed hypothesis test. Is it greater than, less than, is it greater than, or is it just different or not equal to? Next, you need to draw a sample from the population, right? And calculate our sample statistics. We need the sample size, we need the sample mean or the sample proportion. Then we're going to determine the likelihood of observing a sample statistic, either a mean or a proportion, at least as extreme as the one you found under your null hypothesis, okay? And the precise probability of such an observation is going to give you your p-value. And then we decide whether to reject the null hypothesis either at the 0.05 or 0.01 significance level. Those are our only options. That's it. So, in the United States, the average car is driven about 12,000 miles each year. The owner of a large rental company suspects that for his fleet, the mean distance is greater than 1,200 miles per year. He selects a random sample of 225 cars from his fleet and finds the annual mileage for his mean is 12,375. So, let's state our null hypothesis. So my null hypothesis is that my mean equals 12,000 miles, right? Our null hypothesis is the same as the original assumption. And my alternate hypothesis is that our mean is greater than 12,000 miles, right? And this would be right-tailed. So a calculation shows that if you assume the fleet mean is 12,000 miles, then there's a probability of selecting a 225 car sample with a mean annual average of at least 12,375 miles is 0.0099. Now that's really tiny, right? That's statistically significant at the 0.01 significance level. So we can reject the H naught at the that's supposed to be an at the 0.01 significance level. Okay, significance level.